Hello friends, welcome back to another video on transmission gates. In this lecture, we will try to implement all the logic gates using transmission gates. Okay, like we have done in the previous videos, we have implemented the pass transistor, we have implemented the logic gates using pass transistors. Now we are going to implement the logic gates using transmission gates. Okay, first of all, let us take the AND gate. Okay, so what is AND gate? A, B, Y, 0, 0, 0, 1, 1, 0, 1, 1. So my AND gate output is 0, 0, 1, right? So if I wanted to implement the same thing by using a pass transistor, then I know that I have a simple diagram, right? So what was the diagram for us? I will be having a PMOS, I will be having an NMOS transistor here. Okay, this is our basic diagram, Y and A. Okay, what we will do, we will divide the truth table. So when A is equals to 0, what is my Y? When A is equals to 0, Y is always a 0. Right, that means I have connected it to a ground. Okay, when A is equals to 1, Y is nothing but B. Right, so once you give this input, now convert this pass transistor into transmission gate. How to convert? Just because I have a PMOS, I will be adding an NMOS transistor here. Right, because I have an NMOS, I will be adding an PMOS transistor here. Okay, so if A is the input here, then A bar and A bar will be the inputs here, right? So this is the implementation of the AND gate using transmission gate. Now let us see which transmission gate. Let us take this transmission gate as 1 and transmission gate as 2. Okay, so what happens with this? So when A is equals to 0, when A is equals to 0, okay, transmission gate 1 will be equal to, when A is equals to 0, if you see, transmission gate 1 will be equal to on. Okay, you see here, because PMOS for A equal to 0, PMOS will be on, and for A bar means A bar equal to, that means it will be equal to 1, and for a 1, NMOS will be equal to on. Okay, and the same thing, this will be off, this will be off. Okay, transmission gate equal to on and transmission gate 2 equal to off, correct? So what happens, whatever the input is present here, that will be going to the output in this way. That means whatever, if you have a ground, then ground will be going. Okay, 0 is going to the output when A is equals to 0. Similarly, when A is equals to 1, okay, transmission gate 1 will be equal to off and transmission gate 2 will be equal to on, right? So same case, so whatever the input is present here, okay, transmission gate 1 will be off now, this will be equal to on, right? So because this is on, now this B will be going to the output, right? So I hope you understood the concept. So let me draw once again the same AND gate, okay, for your just easy understanding. So instead of pass transistors, what we take is, we take two transmission gates, okay, two transmission gates, PMOS and NMOS, and I have an NMOS and a PMOS here, correct? So I will be connecting this thing and I will be giving it to output Y and an input A, right? So what is the, like, AND gate? Here I need to connect a ground and here I need to give it to B. If it is A, then my inputs here, it will be A bar and A bar. So this is the simple implementation of an AND gate by using transmission gates. Okay, now we will try to implement OR gate. OR gate using transmission gates. Okay, so what is OR gate? I have A, B, Y, 0, 0, 0, 1, 1, 0, 1, 1. Okay, 0, 1, 1, 1, right? So what we will do, first of all, our basic structure is we need to draw. I have a PMOS here, I will be having an NMOS here. So again a PMOS is connected here and NMOS is connected here. So this is our basic structure, first basic structure by using transmission gates, right? And I will be giving an input A here. Once I give the input A, then I will divide the truth table into half. When A is equals to 0, B is nothing but Y is nothing but B, and when A is equals to 1, B is nothing but it is always equal to 1. So I will be connecting it to a plus 5 volts. Correct? So this is the implementation of an OR gate. This is A bar and A bar. So this is the implementation of an OR gate by using transmission gates. Similarly, I can implement NAND gate. Let us see implementation of NAND gate using transmission gates. So first let me draw a basic diagram, a PMOS here and an NMOS here, again a PMOS here and NMOS here. I will be connecting these two to output and an input here, right? So if it is A, then this will be A bar and A bar. Okay, what is my truth table for NAND gate? So A, B, Y, 0, 0, 0, 1, 1, 0 and 1, 1. For a NAND gate, it will be 1, 1, 1, 0. Once I divide this one, you can see for this, when A is equals to 0, Y is nothing but always equal to 1, and for A is equals to 1, Y is nothing but B bar. Correct? Y is nothing but B bar. Right? When B equal to 0, Y equal to 1, and when B equal to 1, Y equal to 0, then that will be equal to B bar. Similarly, I can construct a NOR gate as well. So NOR gate. So what is NOR gate? Again, let me draw our simple transmission gates. This is a PMOS. This is an NMOS. One PMOS here, one NMOS here. Both outputs are connected Y, and I will be giving an input here. Okay, if it is A, then this will be A bar and this will be A bar. What is my NOR gate? A, B, Y, 0, 0, 0, 1, 1, 0, 1, 1. NOR gate. NOR gate means 1 triple 0. 1 triple 0. 0 plus 0, it will be equal to 1. So this is 0, 0, 0. Now you can see here. So when A is equals to 0, Y is nothing but B bar, and when A is equals to 1, Y is nothing but it's a ground. Okay, it is 0. Okay. Similarly, I can have an exclusive OR gate. Exclusive OR gate. Okay. What is exclusive OR gate? I will tell you. First of all, let me draw our transmission gate, basic transmission gate. So this is our basic transmission gate. I have an input A here. So A bar and A bar will be my inputs. A, B, Y. 0, 0, 0, 1, 1, 0, 1, 1. So exclusive OR 0, 1, 1, 0. Output equal to 1 for odd number of ones, right? So you can see, so when A is equals to 0, what is my output Y? Y is nothing but it equal to B, and for A is equals to 1, output nothing but it is equal to B bar. Correct? So you can see here, once you know how to relate by using this truth table, then it is easy actually. Correct? Next, I will try to draw exclusive NOR gate as well, XNOR. Okay, so again I will draw my transmission gate, basic transmission gate. This is my PMOS, this is my NMOS, a PMOS here, an NMOS here, Y and A. This is A bar and this is also A bar. So A, B, Y. 0 0 0 1 1 0 1 1. For exclusive NOR it is 1 0 0 1, correct. So when a equal to 0 it is B bar, and when a equal to 1 it is the input is y equal to B. Okay, this is the implementation of the logic gates using transmission gates, right. So hopefully I guess you have understood. Okay, so some might ask a question I have taken a, like we have taken a PMOS here, if you see, and NMOS here, right. So I can have the opposite one also. I can have the opposite one. That means I can take a PMOS, like the reverse structure of this. The reverse structure of this also it is possible. Okay, and also other thing what is possible is I can also give, like here A bar I am giving, here A I am giving, and also A bar I am giving. I can also take, like if I wanted to give an input A here, okay, or else A bar in case. Okay, just you try to map it with the truth table, then everything is correct. Nothing is wrong in the digital design. Okay, only thing you need to take care is the correct output is coming or not. Okay, once we do the changes also, my output should come correctly, right. So this is the concept of the transmission gates, and also we have implemented all the logic gates using transmission gates. I hope you understood the concept. If you have understood the concept, please like the video, share and subscribe the channel. Thank you.